Hi folks, welcome to the optional review session. I'm going to be going over the problems from exam review 1. If you go to the content area of D2L Brightspace, you can find both the complete problem set and solutions, or at least answers for all the problems there. I'm going to go pretty quickly in the video, knowing that some people, if you didn't quite get something, you'll be able to look on YouTube, pause it, play it back in the future. So give me a second here, I'll get set up recording and we'll jump right into it. After each question, I will pause for a minute. I'll also pause the recording just to see if there's questions from the people who are tuning in live. So just bear with me for a sec here and we'll get started. Okay, so just some general comments as we get started. This first exam covers limits and derivatives. It covers all of chapters 2, 3, and 4. And I think my experience teaching this during the normal school year is that sometimes limits are an afterthought once you've been dealing with derivatives for a while. So we'll start with some limits problems. We'll get on to some derivatives and properties of derivatives a little bit later. So question 1 has, I think, a 7-part question here, a bunch of limits. And what I want to do before I just jump into these is review our general strategy for evaluating limits. Anytime we're taking a limit at a point, so like x is approaching a number, infinity is not a number, but these are all numbers here. Our first strategy is to just try and plug in the number directly. And if that works, the problem is done. So a few of these fall into that category here. So the limit of x squared plus 1 as x approaches 1. Well, the first thing I'm going to try is plugging in x equals 1. And I can see that that doesn't make a problem for me. It's okay if x equals 1, then I get 1 squared plus 1, which is 2. And problem's over. So you should always try that first, see if it works out. We will get to some problems a little bit later on where that doesn't work. So here, I'm a little bit more worried that I have a rational function. I could have division by 0. So what I'm going to write here, I'm going to write this. I'm trying out x equals 3 and see what happens. Okay, well then I have 3 minus 3 over 3 plus 4, so 0 over 7, and it's okay if you think about this for a minute. You say, wait a minute, is that a real number? Yes, this is the 0 pizzas and 7 people, right? 0 divided by 7 is 0, and that's the answer to our limit. Now, if I had the reciprocal, if I had x plus 4 over x minus 3, can't divide by 0. It doesn't make sense to say, like, all right, so we have 7 pizzas and 0 people, how much does everyone have? Like, that just doesn't even make sense as a question. So division by 0 is bad. Division of 0 is okay. So this problem's good, and we're done right there. Okay, question C. Okay, so 2x cubed minus 5, it's in the square root. So I am a little bit worried. I have to make sure that I don't take the square root of a negative number. But to me, it looks like if I take 3 and cube it and multiply it by 2, it's going to be bigger than 5. So again, I'm going to try and evaluate it directly by letting x equal 3. And so if that's the case, then our limit would equal the square root of 2 times 3 cubed minus 5. 3 cubed is 27, times 2 is 54. So we have the square root of 54 minus 5. Oh, this one turns out nicely. So square root of 49, which is just 7. Okay, so started with some pretty easy ones. When we get to limit d here, we run into a problem. You can probably see what the issue is. If we let x equal 1, well, I'll get 0 in the numerator, not a problem. 0 in the denominator, aha, that's a problem. Now, if it was just some number, some non-zero number divided by 0, we would actually know that our limit is infinite. It doesn't exist, and it's either positive or negative infinity. For this one, we have what's called an indeterminate form. So if we were to try x equals 1, that results in 0 over 0, which is an indeterminate form. And what that means is we need to try something else. Our library of tricks for dealing with indeterminate form limits really just comes down to factoring. And this first one's a nice one because they've already given us the factored form, right? We can see this common factor of x minus 1 over x minus 1. And so what that tells us here is that our limit is actually going to be equal to an easier limit. It'll be equal to the limit as x approaches 1 from the right of what we would get if we cancel these. Now be careful, I've seen students like cross these off and end up with 0. We're not like making them go away. We're not just crossing them out. What we're doing is we're dividing the numerator and the denominator by x minus 1. If we divide x minus 1 by x minus 1, we don't get 0, we get 1 up top, and we get x. down below. And what's nice is while the original limit was indeterminate, if we tried to evaluate it directly, our new limit is not indeterminate. It's easy, it's 1 over 1, which is just 1. Okay, so that's a nice warm up for the next few problems. It sort of shows us our strategy, which is to factor. So problem E it's a little bit complicated looking here, and it's not an obvious factoring. What this problem E comes down to is a special factoring form. I'll just write it over here briefly. If we have something in the form a squared minus b squared, that can be factored into the quantity a plus b times a minus b. And you're probably used to identifying this for factoring like x squared minus 4 or x squared minus 81, because you recognize those perfect squares. What's less obvious is that other numbers can be perfect squares. So for example, in the last quiz, one of the factors was x squared minus 3. You probably don't think of 3 as being a perfect square, but it is if we consider the factors x plus root 3 and x minus root 3. Right? And in that sense, 3 is root 3 squared, and so it follows this format for factoring. Well, E is a little bit sneaky. First of all, I think you can see if we plug in x equals 1, we get 1 minus 1 on top, 1 minus 1 on the bottom, so that doesn't really work for us. And the key here is to do the following factoring. Similar to this x squared minus 3, x minus 1 is actually a perfect square. We just have to rethink what we mean by square. So if we factor a denominator, we can factor it as root x plus 1 and root x minus 1. And again, if that's not clear, if you're like, oh, I don't know about that factoring. Does that actually work out? Feel free to go do this on the side, fill it out, and see what you get. It will give us our original x minus 1. And this is good because we have a root x minus 1 as a factor in the numerator already. And so we can cancel those factors. And now our new limit is just the limit as x approaches 1 from the left of 1 over the square root of x plus 1. And again, we've turned it from an indeterminate form into one that we can evaluate directly. 1 on top. If we let x equal 1, then the square root of 1 is 1, and we have a 2 in the denominator, and we're done with the problem there. Okay, so this one's a little bit subtler. Thinking about the exam, I could give you a quadratic, for example, that you had to factor in the numerator and the denominator. Maybe there's a common factor that gets canceled out there. That's our tool for dealing with indeterminate limits at this point in the course. Okay, so problems A through E all have to do with limits of a function at a point. So at a specific x value, we're talking about where the function is headed, whether or not they actually get there or not. Parts F and G have limits at infinity. So we could characterize this a couple different ways. We could say that what we're doing is figuring out the end behavior of these functions here. So the end behavior of this function, the end behavior of that function. By the way, F and G are just reciprocals of each other, but they'll give us a good representative of what the possible cases are here. So when we look at limits at infinity, what we should imagine, maybe there's a typo here. Let me just make sure I copied down G correctly. Oh yeah, that's right. So they're not exactly the same. What we're imagining here is a competition between the numerator and the denominator. In a fraction, if the numerator, the top of the fraction, gets very large, then the number as a whole gets larger or gets farther away from 0. If we increase the denominator either towards infinity or towards negative infinity, the number will get closer to 0. So the question is, well, what if both things are increasing? So we have both the numerator and the denominator increasing here. What happens? Well, it really depends on which is the stronger function, and we measure that by looking at the degree of the function. So in this case, we have a degree 2 polynomial in the numerator, and we have a degree 2 polynomial in the denominator, which means that these two forces are roughly equal in strength. Now, it's true, the denominator has 1 added to it. We might experiment, and if you have time on the exam and you're not sure about something like this, you could plug in larger and larger values of x and see what happens. So for example, if we let x equal 1, then we'd have 1 over 2. If we let x equal 10, then we'd have 10 squared over 10 squared plus 1, so 100 over 101. If we let x equal 1,000, then we'd have like 1,000,000 over 1,000,001. And what you're probably noticing, if I can actually write 1,000,000, there we go, no zeros there, is that these fractions are very close to the number 1. So we might already have a hypothesis about what's going on. In general, anytime we have a rational function, so a function made up of like a fraction of polynomials, we can just look at the degree of the numerator and the denominator, and if they're equal, we'll just take the ratio of the lead coefficients. So here's the lead coefficient out in front of x. It's not written, so we assume it to be 1. Same thing here. The lead coefficient is 1, and so our limit then is just 1 over 1. If we had had 3x squared in the numerator instead of just x squared, then the ratio of lead coefficients would be 3 to 1, and our limit would equal 3 instead. Okay, so problem G, also a limit at infinity. In this case, the numerator has greater degree, so it's the stronger force. And when I say that, what I mean is any quadratic equation will eventually grow faster than any linear equation. Same thing goes for higher degree polynomials. Any degree 7 polynomial will grow faster than a degree 6 polynomial. It will overwhelm whatever effect that other polynomial has in this equation. So these problems are often very quick, especially if you just notice that one is higher than the other. So the degree of the numerator is higher, and that means that our limit is not going to exist. So does not exist would be an acceptable answer. And there's this question though, like if x is going to infinity, is this fraction going to positive infinity or negative infinity? Because those are both different ways in which the limit could fail to exist. Well, I think what we can see here is that the numerator will always be positive, right? Because it's positive x squared. And the denominator will also be positive if we're taking x to be larger and larger quantities. So we can conclude in this case that the limit, here's my air quotes under the, there we go, equals infinity, or we can say that it does not exist, depending on the instructions for that particular problem. So here's problem 1. I'm just going to pause the recording and see if there's any questions from the people tuning in live. Okay, folks, so here's question 2. Question 2 is giving us a piecewise defined function, so a function that's made up of 2 different parts. The 2 parts to this function f, one is the line y equals 4 minus x. So thinking about that, that's a line of slope -1 and y-intercept 4. We can just kind of imagine what that looks like, something like that. And then the other part is the line y equals x plus 2. So line of y-intercept 2 and slope +1. So there's these 2 linear parts, but they only are going to be in effect for different parts of the domain here. So the first line will only be in effect for values of x less than or equal to 2. And the second part will only be in effect for values of x that are greater than 2. And so we've been asked a variety of questions about this function. First, what the limit as x approaches 2 from the left is of this function f. And many of these limit problems, we don't need to know what this graph looks like. We could sketch it out if we needed to, but it's unnecessary for this part of the problem. The important part is if we are approaching 2 from the left, well, which part of the function are we on? Well, if we're approaching 2 from the left, that means we have x values that are less than 2. And that tells us that we should be using this part of the function, right? It's right there in the domain of the function. We can use that part for values less than or equal to 2. Okay, so then what that means is we can evaluate the function using that first rule, so 4 minus x, except we'll just allow x to equal 2 here. So 4 minus 2 is 2. Okay, so part B, very similar. We're going to take the limit of the function f now as x approaches 2 from the right. And so if we're approaching from the right, that means we have values of x that are greater than 2. And so we'll use the second rule, the second piece of the function here, to trace in from right to left. Okay, well then we would use the function rule x plus 2. And again, as we get closer to 2, our limit will get closer to 2 plus 2, which is 4. Okay, so we have a left-hand limit, a right-hand limit. We're able to evaluate that just using the algebraic definition for the function here without having to graph it or anything like that. So we have a couple more pieces here. So part C asks us asks us what the limit as x approaches 2 is. So limit as x approaches 2, and now there's no direction. There's no plus or minus. So same function. And this is great because we've already answered this question. In order for the limit to exist without regard to direction, the left and the right-hand limit have to agree, and they do not. So we can say that this limit does not exist. And finally, part D. Part D asks us if f is continuous at x equals 2. And we can say right now no, and I'll say why. There are 3 criteria that we need for a function to be continuous. I'll make some check boxes here. So One, f of 2 would have to exist. Second, the limit as x approaches 2 of f of x would have to exist. And thirdly, these two would have to be equal. All right, so the limit and the function value would have to be equal. Sorry, I ran off the screen there. In order to say that the function is continuous. So let's see, does f of 2 exist? Actually, it does. We can take x equals 2, figure out which domain that's in, or which subinterval that's in. Okay, it's in the first one. Plug in x equals 2, and so y would equal 2 as well, 4 minus 2. So f of 2 does exist. We've just decided in part C that the limit does not exist as x approaches 2, and since one exists and the other doesn't, they can't be equal. In order to be continuous, we need to meet all three of those criteria here. So here's an interesting add-on to this question. So the second part here says f of x equals x plus 2 for any value of x greater than 2. Could we change that coefficient? And again, this is now a new problem, not the one that was on the review packet, but could we change that value so that the function is continuous? And I think we can. I think we can do it by changing it to x plus 0, or just x. And now if we did that, instead of part B giving us that the limit equals 4, well, now the limit would equal 2, right? Because using the second definition here, our limit would equal 2. And then if we did that, well, then the limit as x approaches 2 would exist. It would equal 2. And that's also equal to the functional value of 4 minus 2. So if instead of 4 minus x and x plus 2, we had 4 minus x and x, then we would have a continuous function. And just to kind of illustrate that graphically really quick, so we have this line, y equals 4 minus x, and it looks something like that. Then we have y equals x plus 2. There's another line, right, that's going to like pick up and maybe meet right here, or maybe not, depending on what that constant is. We just pick the constant to be 0 so that those two pieces meet, making the function continuous and drawable with a single swipe of the pencil or marker. Awesome. So I just had a really good question, and it was, if instead of x is less than or equal to 2, if it was just x is less than 2, how would that affect the problem? So just in general, limits tell us where something is headed. Doesn't matter if the function actually gets there. So we don't need to get to x equals 2 in order to evaluate the limit. When we did part B, I'm sorry, I've written over it now with a different problem, but when we got to part B, we weren't actually allowed to get to x equals 2 using this part of the function, and we were still able to evaluate the limit. So my answer is no. For the limit part, it doesn't matter whether it's less than or equal to, or just strictly less than for a problem like this. Now, if this were the piecewise defined function, we still don't know how to evaluate this function at x equals 2. There might be like a third piece, like we could add a third piece and says, oh yeah, this function just equals 17 when x equals 2. So it wouldn't be a very good piecewise defined function without sort of dealing with all possibilities here. But that's a great question about limits. Okay, so on to question 3. Question 3, there are two parts, A and B. Each one gives us a piecewise defined function, and it asks us whether these functions are continuous or not. So again, to review the definition of continuity in calculus, we'll take the left-hand limit and the right-hand limit, make sure that they're equal. If so, then the limit exists at that point. Okay, that's check mark number 1. Number 2, we need to make sure that the function is defined. Can we plug in a value and get something out? And question 3, are those two things equal? Is the limit and the function value equal? So for problem A, I have this line x plus 3 for values of x less than or equal to 2, and 3x minus 1, which is also a line for values of x greater than 2. And so what I want to do is make sure that those two pieces, those two lines actually meet up and are continuous at that point there at x equals 2. So to do that, I'll take the left-hand limit. So left-hand limit, I'll use my first definition. So I'll write it out fully for this first one. So the limit as x approaches 2 from the left of g of x, we'll use our first definition, x plus 3, and letting x equal 2, we get the value of 5. Now let's take the limit as x approaches 2 from the right. We're approaching from the right, we have values of x that are greater than 2, so we'll use the second definition. And when we do that, we get 2 times 3 minus 1. which is also 5. So since those two match up, we're in good shape on the limit part. Second, let's evaluate g of 2. Like, what is g of 2? Well, g of 2 tells us use the upper definition, right? That's the one that we should use for when x equals 2, and plug it in. Well, g of 2 is 2 plus 3, so it's 5. And we can see that the limit exists because the left and the right-hand limit are the same. The function exists. We're able to plug in x equals 2. And importantly, those two things are equal. The limit and the function value are equal. Let's see what happens with f of x in part B here. So f of x has two parts, one of which is a parabola, x squared plus 3, and one of which is a line, x minus 1. Same thing, though. We want to take the limit as x approaches 1 from the left of f of x, and we're hoping that that's going to equal the limit as x approaches 1 from the right of f of x. And by the way, if it fails right here, we don't have to bother testing the other criteria, since it needs all three to be continuous. If we find even a single criterion that doesn't is not met, then problem's over and the function is not continuous at that value. Okay, so to take the limit of f of x as x approaches 1 from the left, we're going to plug in 1 into the first part of our definition here, which gives us 1 squared plus 3. Right, so x squared plus 3 is 1 squared plus 3, and so we get 4 for a functional value, and then, or sorry, for our limit. And we take the limit from the right-hand side. We'll use our second definition here, so x minus 1, letting x equal 1, and we get 0. And now, since these are different, the left-hand limit exists, the right-hand limit exists, but they're different, and so the limit as a whole does not exist as x approaches 1, and so we conclude that it is not continuous at x equals 1. F of x is not continuous. Okay, so we're on to question 4. Hopefully everyone can see my shared screen here. There's a very tiny diagram. We're asked a sequence of questions about the graph here. Interesting looking graph. They ask us about some limits and some continuity things. So let's just run through this real quick. Unfortunately, I can't really draw on the screen. I don't have a tablet to do that, so I'll have to just talk through these. So part A, the limit of g of x as x approaches 3. So I'm going to locate x equals 3 on the graph here. And sure enough, it looks like there's a limit. Really, the important thing would be to trace along the graph from the left and the right and make sure that they are both approaching the same point. So that limit exists, and it looks like it equals 0, right? Because from the left and the right, the y values are getting closer to 0. For part B, the limit of g of x as x approaches 4. This is a subtle point here. So I don't know if you guys can see. Hopefully, I'll zoom a little more on the graph here. On the graph, we can see that there's this parabola with a missing hole, and then there's a hole up here on the y-axis. The functional value, like the part of the function, is right here. It's at 4, 1, and there's this missing hole here. So, so the question is, how does this affect the limit? Well, again, the limit doesn't tell us where we end up. Where we end up is at y equals 0. But as we approach x equals 4, the y values are getting closer and closer to something down here. Now, this graph isn't fantastic. It doesn't continue the scale underneath here. To me, it looks like it's maybe less than negative or greater than -1. Maybe it's like, I don't know, about -1/2. If this were given to you on an exam and you put -1, I'd give you full credit for it. So again, because as we follow from left to right and right to left, the arms of the graph are pointing towards y equals, I don't know, -1/2 or 1, we would say that that limit is 1 or -1. Okay, so part C, the limit of g of x as x approaches 0. So now we have a little bit of a problem here. As we approach 0 from the left, we're getting closer and closer to y equals 1. But as we approach 0 from right to left, we get this vertical asymptote looking thing that's pointing up toward the y-axis. Those are headed in totally different places. And so we would say that this limit does not exist. And it's also like, it's not that it doesn't exist and equals infinity. It doesn't exist. There's no agreement between the two parts here, between the left and the right-hand side. Okay, so let's see, part D. Part D, the limit as x approaches 2 from the right of g of x. As x approaches 2 from the right, we're going to be on this parabola, like this right-hand parabola here, getting closer to the filled-in dot. The filled-in dot has y-coordinate 2, and so that's our limit from right to left, so approaching from the positive direction. And approaching from the negative direction, we're going to be on that upper parabola, right, the one that's connected to the hole in the graph there. And those y values are getting closer and closer to 3. And again, with the limits, it's not relevant whether there's a dot, filled in dot, or a hole in the graph. We're talking about where the function is heading rather than where it actually ends up. Okay, so F and G are some important concepts in calculus as we move forward. We're asked about when the function is not continuous and or not differentiable. So continuous, we have a formal definition of continuity involving limits and function values. But when we have a graph like this, we can really just ask ourselves, could I draw this without picking up my pencil? And well, we could until we get to x equals 0. So at x equals 0, we have a discontinuity. In fact, we have a type of discontinuity that we call an infinite discontinuity. There's an asymptote in the graph. We'd have to stop drawing, pick our pencil up, and start drawing the next piece after moving over y equals 0. So there's one discontinuity at x equals 0. There's a discontinuity at x equals 2. We'd have to pick up our pencil and drop it down from y equals 3 to y equals 2. So there's another place. Sometimes we'll call that a jump discontinuity. So x equals 2. And then at x equals 4, the graph is also discontinuous. We'd have to pick up our pencil momentarily, put it back down on the x-axis, and then bring it back to that parabola in order to draw that by hand. So there are 4 values for which the function is not continuous. Okay, last part here, it asks about differentiability. So differentiability means, can we take a derivative at this point? In order for a function to be differentiable, it has to be defined. There has to be an actual function value. It has to be continuous. So we've already eliminated 3 possibilities. And then finally, to be differentiable, it can't have a sharp point. So it can't be a cusp or like the corner of an absolute value graph. Those are points on a graph that are not differentiable. And hopefully it makes sense. I'm going to switch over to the webcam here. Hopefully that makes sense, because if we had like a sharp point like that and we're trying to draw a tangent line, well, that's a tangent line, but so is that, and so is that. At a sharp point, there would be multiple tangent lines. And so since there's no good answer as to what the tangent line would be, if we have a sharp point, we also say it's not differentiable. So I think because the function is not continuous at these 3 points, they're definitely not differentiable either. And then looking in the graph, there are no sharp points, and these are the only discontinuities. So F and G, same answer here. So for question 5, we've been asked to use the limit definition of the derivative to find the derivative of the following functions. And I'll tell you right now, don't bother with part B or part C. Part B and part C require some tools a little bit beyond the scope of this class. We never really cover those tools during the semester, but they're really not important to the overall content in the course. So I'm really going to just focus on question 5A. And you should also know that on the exam, if I gave you a question using the limit definition, it would not be anything trickier than maybe question A here. The reason is, when we use the limit definition of the derivative, we always end up with an indeterminate form, one of those 0 over 0 derivatives that we saw a little bit earlier in the review session. The functions B and C require some additional techniques, basically some extra algebra in order to work with. And it's not really worth our time to delve too deeply into those because of how little the limit definition of the derivative functions later on in the course. But I will do question A. So question A says that f of x equals x squared minus 4. And we're basically asked to find f prime of x, but using the limit definition. So let me write the limit definition here over on the side. So f prime of x equals the limit as h approaches 0 of, and sorry if I'm going off the screen, I'll move it over in a minute, f of x plus h minus f of x all over h. And the idea with this limit is that we're starting with an average rate of change, like 2 points on a curve, and making a secant line between them. And then as h gets smaller, h is that horizontal gap between the points. So if we shrink h down to 0, the two points on the curve get infinitely close, and instead of an average rate of change, we have an instantaneous rate of change at that point. So this is all we need to do here. What's referenced in the question is a 4-step process that shows up in the textbook. You do not need to follow that if you're able to do this another way. What we need to do is write this limit and then evaluate it. So, so let's do that. So f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And all you really need to do to make it specific to this problem is to use the rule for the function that we're given here. And the rule says whatever the input is, square it and then subtract 4. Right? That's what this function f does. So f of x plus h means take the quantity x plus h, square it, and then subtract 4. So let me write that out. I still haven't evaluated my limit. I'm going to keep the limit notation until almost the end here. And so f of x plus h. So, okay, so f of x plus h would be the quantity x plus h squared minus 4. And I just want to pause there and make sure everyone's on board with that. So the function f of x says take whatever the input is, square it, and subtract 4. What's our input? Our input is x plus h. And so I take x plus h in parentheses, square it, subtract 4. That is the first part of my difference quotient here. Okay, so there's f of x plus h. Now we need to subtract f of x. Common mistake is that people only subtract part of f of x. To make sure I don't make that mistake, I'm going to put all of f of x in parentheses here. Okay, well, what's f of x? F of x is x squared minus 4. Okay, so it looks like a mess. If you tried to evaluate this directly by plugging in h equals 0, we'd end up with x squared minus 4 minus x squared minus 4 all over 0. We'd get 0 over 0. So to evaluate this limit, we're actually going to have to do some algebra. And the algebra is not so bad. I am going to have to square out that x plus h squared. I won't do it in the video, but you might need to do this over on the side using FOIL or grid to expand it. When we do that, we get x squared plus 2xh plus h squared. So that's our first part here, our x plus h, the quantity squared. We still have a minus 4. And then, whoops, we're going to subtract x squared minus 4. And then this whole thing is still over h. And people are already getting nervous because we're supposed to be making this nicer and it's getting more complicated. But what's good here is you always end up with a bunch of cancellation. So for example, here we have an x squared. And then if I distribute that minus squared, we're going to have a minus x squared. So those two terms will cancel. And I have a minus 4 here, and then I subtract minus 4, so that's adding 4, so the minus 4 and the minus 4, those cancel, right? Let's see, what else do we have then? So already we've cleaned it up quite a bit. So now our limit as h approaches 0 will be for the quantity 2xh plus h squared over h. And unlike in the previous step, now we can actually just divide each one of these terms by h. And now, instead of being an indeterminate limit, it's one that we can evaluate directly. So if I divide out that h, I'm left with a 2x plus h. Letting h equal 0 is no problem. And so here is the result of our limit. And we already knew that, right? We knew what the derivative of x squared minus 4 was. We could just do that using some of our more recent techniques. So it's nice that it ended up with what we knew it was going to be. If you're told to use the limit definition and you just write the derivative because you know what the derivative is, you'll get very minimal credit for the problem. So if you're told to do this specifically, do it. If you're not told to use the limit definition, why would you ever do it? It's way more complicated than the techniques we have recently. Okay, so for the next problem, I've picked a few from the collection of derivative problems that I think are most interesting or instructive. I may do one more after I've done these four. So again, in the review packet, these are the problems from question 6. And actually, I'm going to draw your attention to one thing. Actually, I'll come back to it. Never mind. I'll come back to it. I'll make this point somewhere else. There's some trick questions in among these derivatives here. Not that we're trying to trick you on the exam. But let's take a look here. So problem B, we have g of t equals 2 over root t plus 4 over the square root of t cubed plus 2. I don't know if this is a trick question, but one way to do this problem would be to use the quotient rule and then the chain rule on t and make just a mess out of this problem. But if we just rewrite this problem using exponents instead of roots and fractions, the problem becomes really easy. So the square root of t is just t to the 1/2 power, and dividing by t to the 1/2 power is the same as multiplying by t to the negative 1/2 power. So just by rewriting this as 2t to the negative 1/2, I've avoided having to use quotient rule for this first term here, and that helps a lot. Same thing with our second term. So t cubed, that's the third power. If we then take the square root, our properties of exponents say that we can multiply those exponents. So t cubed, taking the square root, is t to the 3/2, and it's in the denominator, so we'll just write that as 4t to the negative 3/2, and then plus 2. Now, I haven't taken any derivatives, no calculus yet. I've just rewritten g. And so now when we take g prime of t, it's much easier. Negative 1/2 comes out in front, and we end up with negative t, right? Because a negative half times 2 is negative 1. If we take the exponent negative 1/2 and subtract 1, then we get negative 3/2. And then add 4 times negative 3/2. I bet I could do that, but why bother? I'll just write it like this. We don't make you simplify. Negative 3/2 times 4t to the negative 5/2, right? That's what happens when we take negative 3/2 and subtract 2 more halves. And finally, the derivative of 2 is 0, and so we're done with the problem, and our answer is g prime of t equals negative t to the negative 3/2 plus negative 3/2 times 4 t to the negative 5/2. And again, if you simplified it, that's fine. I'm just trying to move quickly here so we can get to as many problems as we can. All right, problem C. Okay, so again, similar strategy. I'm going to rewrite all my t's using exponents. So we'll just say that this is t plus, so t plus 2t to the negative first plus 3t to the negative second plus ln 2. Okay, so here, this is a trick question a little bit, or at least the ln 2 is a little bit of a trick. We just learned about the derivatives of the natural log function this week. And so you might be thinking, oh, I know what that is. It's like 1/2, or it's like 1/2 and some chain rule thing. No, natural log of 2 is just some number. I don't know what the number is, but I know that it's a number. I know it's a constant. So when we take a derivative here, the derivative of ln 2 is going to be 0. And so our overall derivative then, f prime of t, we'll just go term by term. So derivative of t is 1. Derivative of 2t to the negative first is minus 2t to the negative second. And the derivative of 3t to the negative second is negative 6t to the negative third. And then that ln 2 just goes to 0. So there's my answer for C. I'm going to skip a couple here and look at problem F. So I think D and E, one is a product rule problem, one is a quotient rule problem. There are lots and lots of examples of those in our notes, in the videos, online, so I don't think it's really worth our time here. F is a chain rule problem. I'm going to do this just because I know we didn't do a video specifically about chain rule, at least not a live session about it. So again, the idea is that we have an inside function and an outside function. The outside function is like the outer layer, the inside function, g of x is the inside layer, and this is, usually we write it as f of g. The important thing is what we're going to do, if I were to just cover this up, if this was just something to the 5th power, we know that the derivative of something to the 5th power is 5 times that something to the 4th power, right? So if it was like x to the 5th, it would be 5x to the 4th. Well, it's not x, it's this other function here. So it's 2x squared plus x. And then what the chain rule really says is like, okay, that's all well and good, but the inside function is also changing. And so by the chain rule, we also need to multiply by the derivative of the inside function. The derivative of the inside function is just 4x, right? That's the derivative of 2x squared plus 1. And we're done. So if we're using the symbols in which you originally learned the chain rule, this is that f prime of g right here, and this is g prime. I didn't write that out just because the function f was already being used in the problem. I didn't really want to make it confusing. Okay, so problem G. And bear with me, I'm going to erase some of the work from B, C, and F. If we want to come back to that later, I'm happy to recopy it. Problem G is interesting. Problem G is a problem that you could do in several ways. You could use rules of derivatives. So if we did that, I see a quotient rule and maybe a chain rule hanging out in there. So low d high. Low d high is not bad. It would just be this times 3. Minus high d low. So here's high. D low we might need to do over on the side. And then minus low squared. So I bet I can write that out. Let me write it out as if we didn't know logarithmic differentiation. So low d high would be 4z minus 2 to the fourth power times the derivative of the top, so times 3, minus high, so 3z plus 2, times the derivative of the lower function. I'm running out of room here, so let's see, what would that be? So times 4, I'm going to have to cheat here, just like go down here a little bit. So 4 times 4z minus 2 to the third power times the derivative of the inside 4. It's getting a little bit messy, and then the whole thing is over 4z minus 2 to the 8th power, right? Because we'd be taking the lower and squaring it. It's kind of a mess. It wasn't really hard, but problem G here is actually a good candidate for doing logarithmic differentiation. And I just want to show that because it's a relatively new topic. It's not really on the exam per se in the way that other topics are, but it doesn't mean you can't use it. So if I have G of Z equals this thing here, logarithmic differentiation says, okay, well, let's do the following. Let's take the log of both sides. So let's take natural log of G, and we'll take natural log of this fraction, so 3z plus 2 over 4z minus 2 to the fourth. Okay, now properties of logs say when you take the log of a quotient like this, we can actually write it as two different logs subtracted. So this is the same as ln of 3z plus 2 minus ln of the quantity 4z minus 2 to the fourth power. And another property of logs says if we have taken the log of something to a power, that power can actually come out in front. And so if we apply that, we actually get this equation here, log of G equals natural log of 3z plus 2 minus 4 times the natural log of 4z minus 2. And my claim is that this is actually pretty easy to take the derivative. There's a very tiny bit of chain rule, but when we take a derivative here, the derivative of natural log G is just 1 over G times G prime. The natural log of 3z plus 2, okay, well, the derivative of the natural log function is 1 over our inside function divided by the, times the derivative of the inside. So we have 3 over 3z plus 2 minus 4. And again, taking the derivative of natural log 4z minus 2, that's 1 over 4z minus 2 times the derivative of the inside function. And so we're almost to G prime. To get G prime here, we just now take this quantity and we've multiplied both sides by G. So both sides times that original function, 3z plus 2 over 4z minus 2 to the fourth. Okay, so again, I don't know which one's necessarily easier here. They both, like one requires more algebra and less calculus. This one requires just quotient ruling. It's a little bit messy, but it is one of those problems. If you see a problem where there's just like tons and tons of chain rule and quotient rule and product rule all together, those are problems that are a good candidate for logarithmic differentiation. If you're still not quite sure about logarithmic differentiation, look at the last video that I posted, not the quiz review, but the one before that. I did a logarithmic differentiation problem in a little bit more detail than I just showed here, if you'd like to see more steps. Okay, so a very common application of derivatives that we'll ask you to do for a variety of curves and relations is to find a tangent line to the curve at a particular point. Problem 7 asks us to find the equation of the tangent line to the curve f of x equals 1 over x at x equals 2. You don't need to know what the graph looks like, but I'll just sketch it down here so we have a sense of what's going on. The graph of y equals 1 over x is a hyperbola in two parts here. So these two curves are both part of the function. And at x equals 2, let's see, x equals 2 would be right here. So we're talking about a line like this. And sometimes I like drawing or visualizing this just as a check later on when I find my answer. To me, it looks like we should be expecting a line with a positive y-intercept and a negative slope. So hopefully that's what we'll get here. So in any problem that we need a tangent line, and really any line, but a tangent line in particular, we need two things. We need a slope and we need a point on the graph. And then we'll just use point slope form. Okay, so the point on the graph, well, let's see, we have x equals 2, and so let's see what the y value is that corresponds to that. F of 2 is 1 over 2, so then our ordered pair would be the pair 2 comma 1 half. Okay, so we're halfway there, we got the point. In order to find the slope, we know that the derivative gives the slope of the tangent line at any point, so let's take f prime of x. And well, 1 over x, that's just x to the negative first power. And so f prime then, we'd have the negative 1 come out in front. The power of x would drop down by 1, so negative 1 x to the negative second. And the way you usually see this written in a book would just be like x to the negative x to the negative second power. I'm going to write it a couple more ways, not that these are better, but just to make sure that it's really reinforced what we're talking about here. So x to the negative second power, that means 1 over x squared. And when we're plugging something in, that might actually be the easier way to think about it. Okay, so we want the slope of the tangent line at the point x equals 2. So let's evaluate f prime of 2. F prime of 2 is negative 1 over 2 squared, so negative 1/4. And looking back at my graph here, that looks reasonable. It's definitely got negative slope, and a slope of negative 1/4 would mean we'd have to go over 4 units to drop down by 1. And again, this isn't an accurate graph, but at least it doesn't contradict what I was expecting to see here. So last part, I'll write this out too, the point slope form of a line, y minus a known y value equals the slope times the quantity x minus the known x value. So that ordered pair that is on the graph, that point that's on the graph, that's my x1 comma y1, and then m is the slope of the graph. So for this particular problem, the equation for my tangent line would be y minus 1/2, right? That's my known y value, equals negative 1/4 times x minus my known x value, so x minus 2. And I'm done. Leave it like this. Don't need to put it in y equals form or anything else like that. Okay, so I'm going to skip problem 8 and move on to problem 9 here. Problem 9 asks us to find y prime or dy dx using implicit differentiation. If it doesn't say to use implicit differentiation, it's worth taking a look and seeing if we can solve this explicitly for y. Like, can we get all the x's on one side? Well, we could get the x squared over on the other side. We could divide by 4x, but there's no real way that we could just solve this for y. So we are going to have to use implicit differentiation. When we use implicit differentiation, what we're really doing here, I'll just make a little bit more room in the problem. We're taking our equation and we're taking d dx of both sides. So d dx of the left and d dx of the right. And I'll do the easy part first. d dx of 12 is 0. So it's 0 on the right-hand side of the equation. And then to find d dx of the expression here, we'll just go term by term. Well, d dx of x squared is just 2x. That's easy. This is not easy. So what I'm going to do, and I encourage you to do this too, I'm going to punt it downfield. I'm going to say, you know what? That's something that's hard. So let's do that in a separate step instead of like trying to get it all done at once. So we'll just do that there. Okay, now how about the d dx of negative y squared? Okay, well, negative x squared is equal because we're differentiating with respect to the same variable that we're looking at. Y is actually a function of x. Like if this were f of x, if I had f of x squared, you'd know to use the chain rule. The 2 would come out in front. We'd have 2 times f of x times the derivative of f of x. So we're going to do the same thing here, treating y as if it's not just a variable, but it's a function where x is affecting it. So we have minus 2 times y. Sorry, we're running out of room here. So minus 2 comes out in front. Exponent drops down from 2 to 1. Chain rule says multiply by the derivative of the inside function. And this happens, like when we do implicit differentiation, we're going to end up with an equation that has x's, y's, y primes. That's not an issue here. That's actually how things should end up. Okay, so I did punt something downfield. It means I'm just going to evaluate this derivative separately. And I'm going to think about this as a product, right? As the product 4x times y. Could have done 4y times x. It doesn't really matter. They're equivalent. But the important thing is we have x's and y's being multiplied. So you know what? Actually, I'm going to do one more thing. Make our lives a little bit easier. We do know that we can factor out any constant multiple. So I'll actually factor that 4 out and just take d dx of xy to simplify things here. I'm going to do it over here. So d dx of xy not knowing how complicated it might end up. Okay, well, product rule says take the first times the derivative of the second. So we're going to take x times d dx of y. Well, d dx of y is y prime, right? That's what we mean. d dx of y is y prime, or dy dx. We'll add that to the second. So add that to y times d dx of x, which is 1. And so what we get then, as this little side problem, is that the derivative of xy is xy prime plus y. Okay, now I'm just going to insert that into my equation here. And so my new equation then is 2x minus 4 times x y prime plus y, right? That's what I just replaced for the derivative of xy, minus 2y y prime equals 0. If you get to this point, you've made at least half credit. You have successfully done implicit differentiation. The rest of the problem is just algebra. And it's not terrible algebra, but it's not particularly easy algebra either. Our goal then is to get y prime all by itself. I'm going to do that in a couple steps. I'm going to get all my y primes on the right, or that's what I'm going to attempt to do. So I'm going to add 2y prime to both sides. So now the 2y prime over on this side. I'm also going to distribute that minus 4. So we have a minus 4 xy prime, and we have a minus 4 y. I think I'm good here, right? Minus 4 xy prime, minus 4y. I still have a single term involving y prime, so I'm going to also subtract that from both sides. So now on the right-hand side, I have 2y prime, and I guess, yeah, another way of saying it is I will add 4xy prime. So 4xy prime, got all my y primes on the right. What's left over on the left is a 2x minus 4y. A lot of students get to this point and then they're like not quite sure what to do. We can now, the reason we brought all these over to one side is so we can factor out that y prime, and we're left with 2y plus 4x equals 2x minus 4y. And finally, if we just divide by this factored quantity, we'll have y prime all by itself. And so I'll do that. I'll divide both sides by 2y plus 4x. 2y plus 4x. These things nicely cancel. And I'm left with y prime equals that rational expression there. I guess a couple notes here. It's fine to have x's and y's in your answer because their original mathematical relation had both x's and y's. The other thing I would say about this, be careful, don't go any further. You can't cancel the 2's or the 4's or the y's or the x's. Don't start crossing things out. We could factor out a 2 from the numerator and the denominator. It makes me very sad when I have students who do awesome calculus and then they get a little bit cancel happy and just like cross out things that can't be crossed out. So when in doubt, just leave it. Okay, so the final question I'm going to do right now is question 12. It's a related rates problem. And it's really a classic calculus problem. It has to do with a ladder sliding down the wall. So I'm just going to try and illustrate on the whiteboard here what's happening. So we have a ladder of fixed length, and it's sliding down the wall like that. It's falling, basically. And you might think that the various rates of change are the same, like the rate at which the bottom is coming out is the same as the rate at which the top is falling. You just watch the motion there. Like I move the base of the ladder out significantly, and the height only drops by a small amount. And then when we're getting close to the end of the ladder is not moving very much at all, but the top is moving very quickly. So it's an interesting physics problem. It's a great problem to model using calculus. In this one, I'm actually going to draw it down in the corner here. So the ladder, not in our course. So there's the ladder. The ladder is 10 feet long. It's resting along the vertical wall originally, and then the bottom starts getting pulled out. You can imagine yourself at the top. You have your best friend messing with you by pulling the bottom out at a rate of 1 foot per second. Okay, so that's just a drawing of what's going on. And the question is, how fast are you falling if you're at the top of the ladder? Okay, so not really mathematical I've drawn, but I've made sense of the problem. I think that's helpful before we jump into any sort of notation or calculus or derivatives. So if I'm trying to outline how to do these problems, start by drawing a diagram. So I'll say 1, draw. 2, define. There are no variables. I need variables, and I need variables for the things that change. So like the ladder's height does not change, so I can just call that a constant. I shouldn't call that like z or c or anything like that. but the height of the ladder and the base's distance from the wall change. So I'm going to call the distance from the wall x and the height y. There's no particular reason other than like vertical and horizontal. You could call it a and b, whatever you want, smiley face and omega. It doesn't matter. You get to make them up yourself. So I'm defining variables in the context of the problem. Okay, now that I've defined those things, this is a related rates problem. We've been given a rate of change. We've been asked about another rate of change. How do we link these two? Using an equation relating the two variables in play and differentiation. So what have we been given here? What do we know without even applying motion? Well, I know that this is a right triangle. And so based on my drawing here, it must be true that x squared plus y squared equals the hypotenuse squared, so equals 10 squared. Okay, that's just a geometric fact. That's the relationship that we're going to base this problem off of. So moving forward from here, once I figure that out, it's helpful to identify not just what rate of change that I've been given, but to name it using the variables that we have here. So since the distance from the wall to the ladder is given by x, and that's moving, the way that we could interpret this 1 foot per second is that dx dt equals 1. So dx dt, x is the distance, and so dx dt, or x prime if you like, is how that, that distance is changing. And since it's moving away from the wall, that's a positive rate of change. So it's correct to say dx dt is 1. We should also expect that if y is measuring the distance to the top of the ladder is falling, so dy dt, that's really what we want, right? That's the answer to the problem. We should expect that dy dt is probably going to be negative. Okay, so here's the rate that we have, here's the rate that we want, and then here's a relationship that's going to help get us there. So sometimes this is a geometry formula, sometimes it's a similar triangles type of situation here. There's something usually geometric that links our two variables. Make a little bit more room here. So what have we done? We drew, we defined, let's see, what did we do? What else did we do? We wrote an equation. I wish it started with a D, so this would be cool, like alliteration here. So we found a relationship between variables, right, between our variables. And now what we're going to do next is differentiate. I'm really regretting not having another D word for step 3. I'm going to do step 3s. All right, for step 3. Okay, so I'm going to take the derivative of x squared plus y squared equals 10 squared using implicit differentiation. So I'm going to do d dt of x squared plus y squared and take d dt of 10 squared. Okay, so 10 squared, don't be fooled because there's a square, the 2's not coming out. That's a constant. So left-hand side is 0. Sorry, right-hand side is 0. Left-hand side, differentiating x squared with respect to t. Anytime there's a mismatch, we're going to assume that x is a function of t and use the chain rule. So our first derivative here will be 2 times x times dx dt. Okay, so that's the derivative of x squared with respect to time using implicit differentiation. Likewise, when we take the derivative of y squared with respect to time, we'll get 2 times y times dy dt. Okay, so this looks a little bit like a mess. We have x's, y's, dx dt, dy dt, and we're going to need to plug in 3 of those things because in the end, what we want is we want dy dt. So we want to solve for dy dt. So we'll need to know x, y, and dx dt. But we do know dx dt. We know dx dt is 1. And now the question is, can we find x and y? Well, the problem, I've got to go back to the problem here. So it asks how fast the top of the ladder sliding down the wall will be when the bottom of the ladder is 6 feet from the wall. Aha. So they're telling us x equals 6 at some moment in time. Okay, well, if x is 6 and the ladder's height is 10, we can use Pythagorean theorem to solve. So 6 squared plus the ladder's height squared would have to equal 10 squared. And so 36 plus y squared is 100. Subtract 36 from both sides, we get y squared is 64. And that tells us that y must be 8. So to finish the problem now, we're going to plug in for x, plug in for y, and plug in for dx dt, and we should be able to solve this for dy dt. So let's do that. Plug in x equals 6, so we have 2 times 6 times dx dt, which is 1, plus 2y, so y is 8, so 2 times 8 times dy dt is 0. Okay, so what does that give us? We have 12 plus 16 dy dt equals 0. Subtract 12 from both sides, I get negative 12 is 16 dy dt. Apologize for messy workflow here. And then finally dy dt is going to be negative 12 over 16. You can leave it like that. It reduces to negative 3/4. And that makes sense that it's a negative rate of change since the height of the ladder is decreasing. Yeah, that jives with the problem. Maybe just to finish this strategy thought here, I started with this kind of checklist. We drew the problem, we defined variables, we found a relationship between variables. It was the Pythagorean theorem in this case. We differentiated, and then what we did is we plugged in. Right? So we plug in and solve at that point. One of the biggest mistakes that I see in these problems is that people want to plug in immediately. So imagine if we did that. If we just said, okay, x equals 6 for the problem. Well, if x equals 6 and is unchanging, well, the ladder isn't falling at all, right? And if you start taking derivatives, letting x equal 6, all your derivatives are going to equal 0. So in any problem, if you're going to have to evaluate the derivative at a certain point, plug something in, make sure you take the derivative first and then plug in second.